Let's go ahead and talk about the collision model and how collision model accounts for reaction rates. What is the collision model? Well, we have two observations. First, as we increase the temperature of a reaction, this increases the rate of reaction. Second, as we increase the temperature of reaction, it increases the magnitude of the rate constant K. The larger the K value, the faster the reaction goes. Photographer's rule of thumb, for every 10-degree increase in temperature, the rate of a reaction approximately doubles. The collision model helps us understand why increasing the temperature increases the rate of reaction. So I want you to consider the following reaction. A plus BC going to AB plus C. A is its own individual molecule and BC is some kind of thing by itself, molecule, element, whatever, and then BC is a compound together. They come together, they react, they form AB, and then C is left off on its own. Suppose this reaction occurred in one elementary step. What would happen is particle A would come in, it would collide with particles BC, it would undergo a transition state, and then they would leave with AB being bound together and C being bound by itself. So, A and B, C have to come together. They have to collide in a certain order. They have to collide with sufficient energy and the proper orientation in space. During this transition state, this is where I am breaking the bond between B and C. I am forming the bond between A and B. Once broken between B and C and formed between A and B, the particles move off in their own directions again. This is what I mean by the collision model, though. A comes together with BC, undergoes some kind of transition state, and then once complete, A and B go off on their own direction, C goes off in an opposite direction. The collision model, though, illustrates three principles. In order for reaction to occur, the molecules must, in fact, collide. In order for reaction to occur, the molecules must collide with sufficient energy. They can't just kind of come along and be like, pop, nothing's going to happen. But they can't come along with so much strength and force that they destroy each other either. They have to be the right amount of energy for the reaction to occur. They also must collide with the appropriate orientation in space. Not only must they collide, because otherwise if they don't collide, they're never going to come together, right? Nothing's going to happen. They must have enough, enough energy when they collide, but they must have the appropriate orientation. So, shown here, orientation of particles. Before the collision, we've got these particles coming together, NO2Cl with a Cl molecule. These two molecules come in, they collide, but the orientation of this collision cannot produce a Cl2 molecule. This reaction is taking NO2Cl plus Cl and giving me NO2 plus Cl2. If I have the oxygen and chlorine colliding together, that's not going to produce a Cl2 molecule. So after the collision, no reaction has occurred because they didn't have the correct orientation in space. Now the second example, before collision, the NO2Cl molecules coming in, the other Cl molecules coming in, and the chloride molecules do in fact collide. When they collide, they're in the correct orientation in space. So after the reaction, after successful collision, off goes NO2 in its direction, off goes Cl2 in its direction. This was a successful collision because they collided with sufficient energy, but they also collided with the appropriate orientation in space. So another example, very similar to the one we just looked at, if I look at Cl plus NOCl, giving me NO plus Cl2. I've got Cl, and this is coming in with Cl bound to an N, bound to an O. When these two come to each other, these chlorides are oriented in the right space. They're going to undergo a transition state where the two Cl molecules are going to start to bond and the NO is going to start to release that chlorine. This is your transition state. So the chloride's still coming together, this molecule is still coming towards it. After the transition state, we see a successful reaction where the Cl2 molecule leaves and the NO2 molecule goes the other direction. But if they did not come at the correct orientation in space, so let's say instead the oxygen molecule was oriented towards that chlorine, even if they collided with correct energy, this would come in. The transition state would be that chlorine considering bonding with that oxygen, them realizing they don't want to bond, the transition state being ineffective, and off would go the chlorine atom by itself, and in the other direction would be that ONCl molecule going the other direction. So it's not enough for the molecules to collide. They must collide with sufficient energy and with the appropriate orientation in space, i.e., not every collision is an effective collision. That's why the higher the temperature, the more likelihood of the reaction to be able to go forward, because the higher the temperature means more collisions. The more collisions you have, the more probability you have of successful collisions.